All right, this notebook's going to go through gradient-based optimization. So previously we saw how we could optimize parameters of our models using grid search and random search, but they had some fundamental flaws. One of them was that we had to specify the range which we wanted to search for parameters within, and that might not actually contain the optimal parameters that we want to find. Another one is that these techniques don't use information about any of the previous parameterizations to guide where to search next. So if they find a low value, they don't start searching around those same parameters to maybe see if the other low values are in that region. In random search, they just choose a totally other random value in that space. And in grid search, they choose a predetermined next step at the next interval along each parameter. And another problem is that as the number of your parameters of the model increases, these two techniques, they take exponentially longer with every single parameter to complete. So we're going to try and look at gradient-based optimization as another technique to optimize our models which can overcome these limitations. So firstly, just to cover this, what is a gradient? So imagine a function with an output y and an input x, a weight parameters w and bias b, such that the equation is like this. So our output is some weighted a version of our input plus some offset. So this is the slope, this w, and this is the intercept of the y-axis. So that's just the equation of a straight line. And so the gradient of y with respect to w is the amount that y changes when we increase w by 1 unit and hold all the other values constant. So the sign of the gradient, either negative or positive, specifies whether y will increase or decrease as a result of the unit change in w, and the magnitude of the gradient is the amount by which y actually changes. So the gradient can also be called a derivative. The total derivative of y with respect to w is denoted like this with these regular d's, and the partial derivative is denoted with these deltas like that, these partial symbols. And partial derivative is when we hold everything constant. Regular derivative, it's meant to take account for any variable which contributes to the thing you're looking at the derivative of. It's meant to account for any change in any of those variables. So for example, in this case where we have our function which looks like that, the rate of change of y with w, the derivative of y with w is x, because when we change w by 1 unit, well, the amount which that changes the output is multiplied by the x here. The rate of change of y with respect to x, so the partial derivative of y with respect to x, similarly, if we change x by 1, well then it's going to add one more multiplication of w, and so that's w. And if we, so the last one, find the partial derivative, the gradient of y with respect to b, well if we change b by 1, well, b just adds a single number, a single unit value to the output every time it's increased by a unit. So that's just 1. Okay. And if you're not confident in that fully, just click it. So what's gradient-based optimization all about? What's optimization about in general? It's about finding different parameterizations which minimize some value, some objective, some loss, error, or cost, which tells us how bad the model is. The loss, just like our model, is just a mathematical function, depends on the parameters of the model. And we'd like those parameters to give us a low value of the loss when we evaluate the model on that objective. So if we were to evaluate the value of the loss for every different possible parameterization, we'd produce a loss surface. And basically what this is some surface which is a function of input parameters, which tells you how bad the loss is. So before we go on to surfaces, just look at this where we have a single parameter in this graph here. This orange line would be the loss surface. In this case, we're only looking at one parameter, so there's just a slice of the surface, and so we get a loss curve. But if we had multiple different parameters, we might have some surface that looks like this, and we're going to try and move our parameters or test different parameters across all this surface. Maybe this direction controls the weight, this direction controls the bias, and we're going to try and find the lowest possible value for our loss. So Now, what we want to do, like I said, is we want to find that minimum point down there, or here. We want to find this minimum point. So imagine we put our parameters there. So we set this W equal to this value. Now, as we move W away from this point in the positive direction, the gradient, that is the slope, it becomes more positive, like this. So all the way over here, this is the gradient of our loss with respect to our weights. So how our loss changes with our weights, our partial derivative of our loss with our weights, is positive. As we increase W, the loss will increase. It will go up there. So, but if we move our weights in the negative direction, well, then the loss also increases in the negative direction. That is, it gets smaller. So and at this point, if we increase W by one step, our loss will go down. So we have a negative gradient here and a positive gradient here. A positive gradient when we move the weights positively away from the minima, and a negative gradient where we move the weights negatively away from the minima. And so what we can kind of deduce from this is that as the gradient becomes more positive, we should move the weights in the negative direction to get back towards the minima, right? So if we move our W, the gradient increases, but we want the gradient to stay 0, so we should move them in the negative direction. As we move our W negatively, the gradient becomes more positive. The gradient becomes more negative, which means that we should move W in the positive direction to reduce our loss. Okay. So yeah, just a note here, if we're going to do gradient-based optimization, we need to make sure that we can differentiate the function which our model and our loss function represent. So they can't have maxes or anything like that. So they need to be fully differentiable. So let's start by creating some fake data, just as we've done before. Run this, gives us some data. So this is a straight line which we're trying to fit. Maybe we've collected these data points of some input X and some output Y, and we're going to try and learn to model this function. We're going to try and learn what the best parameterization of the weights, the slope, and the intercept, the bias are. So let's talk now about gradient descent. Gradient descent is an iterative gradient-based optimization technique, and basically what we do, as I kind of indicated here, is we just take some examples, evaluate our model on the examples, find the loss, then find the rate of change of that loss with respect to the model parameters, and then just take a small step in the opposite direction of the gradient to move, hopefully, towards some minima. That's literally exactly how it works. So yeah, here's our algorithm. Randomly initialize the model parameters and then do that stuff I just said. But so we're gonna update our parameters by shifting them in the opposite direction to the gradient. But by what amount should we actually shift them in the gradient? If step size was on constant value, then our model might need to adjust its weights by some value smaller than this to reach a nearby minima. So say we start with our weights here, this W1, and the gradient is this big. Well then, if we move in the and it's positive over here, because if we increase W, the loss increases. So the gradient is this big. Well, if we move it by a step size of that large in the negative direction of the gradient, we're going to jump all the way over here. But that's too big of a step. So now we've gone to this W2, and we're even further away from the optima, this W star, and we're actually diverging, and we're going to go further and further away from the optima. So we need to take steps which are actually smaller than the gradient, so or maybe smaller than just some constant value. And this basically means this is where we should introduce the learning rate, this value alpha, which is a value which we can choose, which we should usually set less than 1, such that basically we don't take steps like this. We don't get our weight and update it by and don't set it to what it was, but minus the whole gradient. Instead, we multiply that gradient by this learning rate alpha, so that the steps we take are just, maybe the gradient is maybe the gradient is larger than that, but then we just take a small fraction of that step. So instead of taking this whole step, we'd maybe just take a little part of that and step down to here. Then our weight will become here, and then maybe the gradient is this big, and then we move just a little bit of that back here. So we basically use the learning rate to control the step size of the updates that we perform using gradient descent. And so this is the gradient descent update rule here. We literally just evaluate the model's performance using the loss on some examples, find how that loss changes as we adjust the weights, and then move those weights in the direction opposite to that gradient, scaled by by a factor, the learning rate, which just controls the step size of those updates. Okay, so here is a case where the learning rate is too large, or maybe we just haven't used a learning rate. Similar problems can occur in either case. So the learning rate's too large and we step all the way over where we actually want to step towards. In this case, the learning rate's too small and we're just going to take ages to converge. We're going to have to take many little different steps all the way down, and they're going to get smaller and smaller as we go, as the gradient decreases, because the loss surface becomes more flat. So it's going to take too long if the learning rate's too small. And here is a case where the learning rate is kind of optimal. So we're taking, it only takes about 3 steps for this to converge. And so this shows that the learning rate is something that we often need to tune. We need to try out different values and see, well, what's the highest value that we can have whilst it still converges rather than diverge all the way like that. And yeah, obviously we can do that in multiple directions at once. So we wouldn't just update one parameter, we wouldn't just update the weight, but we'd also be doing the same for the bias, and we'd also be adjusting that so that our loss decreases. Cool, so like I said, our model and our loss, they're all just differentiable mathematical functions, and this is a walkthrough of calculating the derivatives of those values. And this is for the specific case where we're using the mean squared error loss, as we covered in the last notebook, and our model is a linear model like this. So this is how you compute the rate of change of the loss with respect to the weights. You can walk all through this, end up with this equation, and the rate of change of the loss with respect to the bias is very similar, just not with this x here. Okay, so we're going to implement those now to update our linear hypothesis class. We're going to add this method to calculate the derivatives, and so these are basically this is going to account for us using the mean squared error loss, and then return some values which are the rate of change of our loss with respect to the model parameters. So firstly, this is going to take in our predictions, our y hat, and the labels, as well as the inputs. So the inputs, the outputs, the inputs, our predicted outputs, and the true labels. So let's look at these equations. The first thing that they both contain, you can see, is this difference between our predictions and our true labels. So that's what we'll calculate first. We'll do diffs is equal to y hat minus labels. And then we will, then we need to implement this to find dl dw, so partial L, partial W. Okay, well, what's that? Well, it's 2 multiplied by the sum, do np.sum of the differences multiplied by x. So we can diffs multiplied by x and then divided by this m there. And similarly, just writing down this equation here, the rate of change of the loss with respect to the bias is 2 times np.sum. So that np is numpy, as usual. np.sum of the diffs divided by the number of examples that we have, that we pass through that number of examples in, number of different x's that we produce that loss from, that we evaluated our model on. Okay, so we should be able to run that, and then we're going to actually call that method. So how do we get the rate of change of loss with respect to our weights and biases? Well, we need to initialize that model and then call that method of the model. So I've initialized our model as h, so our hypothesis is a linear hypothesis. Now I can use h's method update underscore, not update, calc derivs, and this takes in our x and our y hat and our labels, which I think that we call y up here. Yeah, cool. Y. All right. Cool, and then we have calculated the rate of change of our loss as we increase the weights by one unit, and the biases by 1 unit. So if we, that's exactly what that means. If we increase our weight by 1, then the loss will go down 13.75%. Sorry, 13.75 units. And if we increase our bias by 1, then our loss will increase by 16.32. Okay, so now we can compute the losses. We're actually going to use them to implement gradient descent. So we're going to use those, once we can calculate those derivatives, we're going to use them to implement gradient descent. So, and here we're going to do that. We're just going to make a train function similar to what we've seen before as well. And then we'll get our derivatives by doing calc deriv on x, our predictions, which we've called y hat, and our labels y, and then okay, so we've calculated the derivatives. Now we need to find what's the new value of the weight's going to be. Well, if we look back here, this is the gradient descent update rule. So we're going to have our new weights are going to be set equal to what the weights are currently, moved by a small amount in the negative direction of the gradient. Okay, so that's what we're going to do here. So our new weights will be h dot w minus, and I've defined a learning rate here, learning underscore rate. So that's our alpha multiplied by dl dw. And then we're going to do a similar thing here. We're going to do our new biases is just going to be, well, what was the bias currently, shifted a small amount by the learning rate multiplied by the rate of change of the loss with respect to the bias moved in the opposite direction to that. So that should be our update rule, and then we'll just use the method of our linear hypothesis to update params, which sets its weights and biases to whatever values we give it. So we'll update the model's parameters with the new weight and the new bias computed using gradient descent update rule. Then we'll call that train function and we'll plot the loss as it goes, and it should look something like that, and run that. Cool. So as we step through the data set, 9 or 10 times here, then this is how the cost changes over time. It's good, it's going down, it tends to 0 in this case, and that's because our model tends to fit the data. So here's all the labels and here's our hypothesis, which are pretty closely matched. A good model of the straight line there. So we've done it, yeah, we implemented gradient descent there. Nice. So why gradient-based optimization? I've already mentioned the issues between techniques we saw before, like random search and grid search. But beyond these, an advantage of using gradient-based optimization is that it follows a heuristic. That's an indication of how to improve. So this heuristic in this case is the gradient, which might be a good way to indicates how should we best change the weights from here. And the way it does that is not just look at the value of the loss, but it says, okay, I tell you the direction which the loss is increasing. That's what the gradient does. It points in the direction which the loss is increasing, and we're just going to move in the opposite direction to that. So it tells us, it indicates what values should we try next. Whereas grid search or random search, they didn't take any, this is what I meant when I said it earlier, they don't use any they don't use any information they have to make updates based on based on some indication of where would be good next. So by using gradient descent, which follows a heuristic indication of where to try next, is down the hill, our model can converge in much less iterations compared to grid or random search. If we initialize our parameters actually right near the optima, then gradient descent might only need a very few updates to reach the best possible parameterization. Whereas grid search or random search, even if they start by trying the best possible parameterization, they're still going to try everything else in the space. Okay, so now why should we not pass the whole data set through the model for each update? So we know that to perform gradient-based optimization, we need to pass our inputs through our model, make predictions, and then compute the error of those predictions using our loss function to find out how it changes with respect to the parameters of our model. And modern data sets can be absolutely huge. They can have millions of examples. And this means that if we're going to pass every single example through, then it might take a long time to compute predictions for all of those. Now, the point of passing through, multiple examples at least, is to get a good estimate of what is the true gradient. What gradient will update my model to perform best on a good sample of the examples. The best possible sample would be all possible examples. If we evaluate the gradient for all of them, then that's pretty good representation, pretty good estimate of what we should actually the true updates that we should make the parameters. So if we pass a full data set through the model at each pass, it's called full batch gradient descent. Okay, so why not just pass a single data point through the model if that's going to be way faster? Well, just as I said, we want to get a good estimate of what gradient should I update what value should I update the parameters with, and that's based on the gradient. So we want to take a good sample of examples. We don't just want to use one, because then the model might just improve for that single example and not generalize to improve for all of the other examples in the data set. So it won't be a representative sample of the gradient. And so passing single examples through the model is called stochastic gradient descent. Now, what we really want to do is something between these two, so that we get both good inference time, so forward pass, when we actually compute the loss, that won't take too long because we're not going to use the whole data set, and we don't want it to be fully stochastic, just using one example, because that won't give us a good representation, a good estimate of the gradient. So that's why we pass in more than one example. So because we want to get a good estimate. So this is called mini batch gradient descent, where we pass several but not all of the examples through the model to compute a good sample of the gradient. And so most optimization algorithms converge much faster if they're allowed to rapidly compute approximate gradients rather than slowly compute exact gradients. And the size of the mini batch is called the batch size. Mini batches are often incorrectly referred to as batches, but it doesn't really matter that much. Now this is just a helper function here. You can walk through the commented code to understand what that does, but basically it batches together small groups of examples in your data set. So it takes in a data set and a batch size, and then it will return you a list of the batches. So, and then when we're done that, I'm going to print the data loader, which is what I've called it. So this is the data loader is our list of different batches, and I'm going to print the length of that. So the original, actually, let's just firstly print the length of the data set. Run that. So originally our data set had 50 items in. Now this is our batch data. So you can see that it's a list of arrays. Like that, I think, and and now that has a length of 13 items because we've used batch size 4 here. Okay, so we're going to pass through 4 examples at a time, and then compute the gradients for these, and then make an update based on them. So we hope we can get an approximate value of a good gradient to make a good update using just 4 examples. Okay, and that should be 13 times faster than having to do the same evaluation of the model's performance on every single example. And so here we just changed our training function above slightly to implement that. So now it also iterates through the data loader, not just through the number of epochs, and it does this for a set number of updates. So I'm doing 10 times as many examples as we have, and and what we're also going to do here is we're going to start timing how long it takes to perform the inference, that is to make the predictions. We're going to time how long it takes to calculate the derivatives, and then we're going to time how long it actually takes to update the parameters. We're just going to compute the inference time and the weight update time. I'm going to do that for 3 different batch sizes. So one is full batch training, where the batch size is the length of the whole data set, so we just have one batch in the data set. Stochastic training, where the batch size is 1. So in this case, we're going to have 10,000. We're going to have 10,000 batches, and then we have the mini batch training case, where the batch size of 32. So the number of updates is going to be between the number of batches in the data set is going to be between 10,000 and 1. So we'll run that. It's going to do this full batch training, iterating through the data loader until it's done as many updates as we specified. Now, we can see here that stochastic and the mini batch training perform inference much faster. That's this value here. Inference is much faster for mini batch or stochastic training than full batch. And this because, as we said, it doesn't have to make predictions for every single one of the inputs. And it's also about 3 times faster for updating the weights if we use stochastic or mini batch training. And the final cost of the stochastic training is actually much smaller, and the same for mini batch training, is much smaller than that for the full batch training. So we've made a lot better progress given the same number of updates. And so for a larger data set, we might see that stochastic gradient descent actually doesn't converge. So in this case, it's like, okay, well, stochastic training has performed better in both inference, where it's performed equivalent to mini batch, and inference and weight update times, but the final cost is actually lower. But in practice, for a more complex data set, stochastic training might actually not converge, and you might not get a final cost as low as you would for mini batch training. So mini batch training is generally what we do. That's where we batch our examples together into groups smaller than the length of the whole data set, but larger than 1, and compute our updates based on the performance for all of those. Cool, so that was it. That was the whole notebook. Covered gradient-based optimization, what it is and why it's advantageous compared to grid or random search, and we've also learned about why it can be useful to load our data set into mini batches, and then we implemented that in code.